Okay, so we're recording. First thing I have to say, I think this is already clear in the recordings that I sent to y'all, but I feel it necessary to say first day class. Everything is going to be recorded in the sense that what is on the screen, right, will be recorded. And there's a microphone somewhere on this laptop computer that'll be recording almost entirely my voice, but for legal reasons, I am obligated to inform you that your voice may be picked up by the recording as well. So anyway, FYI. Practically speaking, by the way, it's very little, and I can't imagine you'd be recognizable. So anyway. Okay, so y'all, I hope all got my announcement from a week or two ago, whenever that was. Pointing out, among many other things, the class webpage. Here it is. The address here is from the email that I sent out. It will be changing because my organizational system for websites is a little bit rusty because I've been using Sakai sites for a long time, and I came up with an idea that I thought made sense, and I've thought better of it since then. So anyway, this will be changing slightly in probably later today or something like that, and I'll send an email out to the class roster when I do that. Okay, so per my recording that I sent, make sure that you click around on all of this, read all of this. If you joined later, make sure that you read this early announcements page, which I don't know why it's not coming up now. Okay, what's going on there? Let's try that again. Okay, so the internet's going slow for some reason. I don't know why. But anyway, if you click where it says early announcements, and if the internet's operational, then you'll find all the announcements that you might have missed. Okay. All right. So I'm with that said, pretty much just dive right in to the notes, and here we are. This is the Math212 lecture notes that you will have found on the website. The first 3 pages here are not multivariable calculus material. They are not Math212 material. This material will not be on any exams or any homework assignments or anything, right? So no stress, no pressure. You don't have to know this business about arrays of squares and 2x1 tiles. This is just kind of an example with which I'm going to try to communicate a really important point about what the nature of this math class is, and I think the nature of really most, college level, sophisticated math classes. So I'm going to start off describing a little problem, and then we'll sort of take it from there. Here we go. So here's the problem. Suppose I have an 8x8 array of squares, like so, right? 8x8. And suppose I have a bunch of 2x1 tiles, like this little thing right here, 2x1 in the sense that one side is of dimension 2, the other side is of dimension 1. Okay, and so that said, if I were to give you 32 of those tiles, of course, clearly you can cover the 64 squares. This is a really easy problem. It's trivial, right? Okay, that's not the interesting question. The question is, if I were to remove the opposite corners with a pair of scissors, and if I were to then also take away one of your tiles. Now, from an area point of view, everything fits. I have 31 tiles, each of which has area 2, allowing me to cover 62 squares, and I have 62 squares. It ought to fit. But does it? Can I actually cover all of these tiles? Can I cover this entire edited board with the remaining tiles? So now you can do what I'm going to call the trial and error approach, and you can sit here and try to, physically do it. And if you kind of basically snake around like this, etc., what you're going to find is that you have this tile and this tile left over, and and one domino, right? one tile with which to cover those 2 squares, and of course you can't. Right? Okay, so then you say, all right, well, I see what I did. I painted myself into a corner. So I'm going to start over, and then but this time then you'll have some strategy in your mind for how you think you're going to not paint yourself into the corner this next time. And yet you will. And then you're going to say, you know what, this is tedious. I'm going to program this into a computer. And maybe you could, right? But even that, I think, would be actually a hard thing to do in a lot of ways. And either way, there would be billions of trials. And you could call that satisfactory in certain ways. But I have a point of view on this to show you in a few minutes. I think we'll agree that even that is in a lot of ways unsatisfactory. So, okay, now let me show you the solution to the question. The solution to the question, I like to call this a creative solution. I'll come back and talk about that in a moment. We're going to apply a checkerboard pattern. The idea of the checkerboard pattern is that sort of every other, diagonally offset square we color black. The remaining stay white. Right? Now, I just made that up. That's not given in the statement of the question. But if you do, notice then that every one of your tiles covers exactly one black square and exactly one white square. And it doesn't matter if it's arranged vertically or horizontally. It doesn't matter where it is on the board. Always, no exceptions, always exactly one black, exactly one white. Okay, that's, I think, a pretty easy pitch, right, from the nature of the pattern. Now, having noticed that, I'm now going to define this expression called I. I'll come back and talk about why I call it that in a moment. I is defined as, for any given arrangement of tiles that you've put down, I is the number of black squares that have been covered minus the number of white squares that have been covered, and since you get one of each every time, this is always 0. Right? Everybody with me? Nothing you can do about it, right? This number is always 0. So, that said, notice that the two squares that we removed, remember I removed this square, and then I removed the opposite square, but because of the checkerboard pattern and because these are connected by a diagonal, these are the same color. Now I've drawn it here as if they're both black. They might be both white. I don't know. Doesn't matter. The point is they're the same. And because they're the same, that means that the total number of black squares and the total number of white squares differ by 2. I don't know which way, doesn't matter. But they're different. Which means that this thing that I defined up here, this thing called I, if I were to be successful and cover what I'm supposed to cover, it would have to be 2 or negative 2. But it can't. It's 0. So this is nonsense. There's no way this is possible. Game over. It's not possible to do this. Is everybody happy? I didn't have to try billions of anything. Okay. So this is a really powerful idea. So now I have a couple of cultural points that I like to point out at a time like this. I call this a creative solution. You see I have this in the notes up here, creative solution, because it is literally creative. This word does not mean what a lot of people seem to think it means. A lot of people think that the word creative is synonymous with the arts. Well, that's just not true. Certainly not. Importantly not, right? We literally created the checkerboard pattern. That wasn't given in the statement of the question. We made that up. If you think about it, if you kind of edit out your previous experience with games, right? It's a very clever, creative construction. But we made up. And then here's the other thing. This expression called I, made it up. Right? That wasn't given in the statement of the question either. So, I like to point out at a time like this that a lot of people have completely misunderstood the nature of math and think that math is about, it's a precision, which is true, yes, absolutely, but that it's precisely applying algorithms and getting to an answer. And that's just not really true. I mean, that's one of many tools that mathematicians use. Yeah, sure. But that's not fundamentally what mathematics is. Mathematics most fundamentally is about creative ideas, creating new constructions in clever ways that accomplish certain tasks, and being able to use existing constructions in creative ways, being able to do different things. That wasn't really quite intended for this, but if I tweak it just a little bit, then it'll do what I want it to do. Right? So creativity is intrinsic and fundamental to what real math really is. And so again, if your high school math classes may not have had so much of that, right? Most high school math classes, I think, are really pretty light on the creativity. Heads up, there's going to be plenty of, I'm going to call it to certain degrees, creative thinking that's going to be required in this course. And creative understanding. You need to be able to understand the, what are the ideas that we're making up? How do they work? Right? And then to be able to use that understanding of those ideas at a fundamental level to then make creative applications of those ideas. So that's just a heads up. Another cultural point I like to talk about is why I called this I. It's because it is an example of something called an invariant. And the higher you go in math, the more you will find these things called invariants being used in very powerful ways. It's pretty cool. So the general idea of an invariant is if you have some circumstance where there's a lot of things that are allowed to change, thus creating a problem. You want to address, in some sense, all of them at the same time, all possible arrangements of dominoes in this case, right? But all possible whatever it is that's allowed to change in your problem. One of the big tools is to think up something that never changes in all of those cases, and then try to figure out how you can do something clever with that, right? So invariance, big deal, really big deal in math. Okay. Okay, so now what does this have to do with tests? Here are some examples of kinds of questions that you might encounter on a test. Example 1 here is the exact question that I just told you how to do. 8 by 8 array, opposite corners removed. Opposite corners removed. Is it possible to cover with the area appropriate number of dominoes? So that's what I'm going to call an easy question. Already told you the answer, right? So all you would have to do to prepare for these kinds of questions on a test, and I emphasize there will be no checkerboard questions on any tests in this class, so that's, don't need to worry about that. But all you would need to do for such a question is make sure you understand the process for that one question, for that one example. There's not going to be a lot of that on our tests. Now the next, let's see here, I've got my cheat sheet down here. Yeah, that's right. So these two examples, what if I were to change the question and make it not 8 by 8 but 20 by 20? Or worse, 750 by 750. Right? So pretty much the same argument would work. It would be a little different, just a little bit, because, well, it's not 8 by 8 anymore. You got to think through a couple of details, make sure that the argument continues to work, but it's an easy adaptation. What if it were 20 by 40? It's not square anymore. Does that change the argument? I don't know. That's your job, right? To think it through. Think through every aspect of the argument that we made with the example that I did do, right? And ask, can this be adapted? Does it work? Do all the pieces fit together? And it's got to think it through. And the good news is on these, it does just fine. So these are what I would call slightly harder test questions. You will be seeing this kind of thing, again, not with the checkerboards, but slight adaptations of ideas that you've seen before is a thing. And that is for sure going to be part of this course. Now, what if it's now 75 by 150? Now, this is what I like to call a landmine question. Because you're walking along, minding your own business. Everything seems like it's going to go just fine and no problem. And yeah, okay, it's not square. It's sort of twice as wide as it is tall. Yeah, okay, no, whatever. We've seen those before. They work out. Are you sure? You got to think through the details. The devil's in the details, as they say, right? And it turns out here that because this number here is odd, it doesn't work anymore. The opposite corners that you removed are not the same color. So the argument crashes and burns. Now, what does that mean? Does that mean that the board is possible to cover? Well, I don't know. That doesn't immediately follow, right? All it really tells you is that your previous argument that we've been kind of adapting and tweaking is worthless. That's all that means. And if one argument is worthless, that doesn't mean that the conclusion, the would-be conclusion that it would have come to is wrong. It just means that the argument is worthless. It means you have nothing, right? And so for this question, what makes this question hard, again, is to realize, first of all, that you can't just kind of go by the aesthetics of the question. A lot of people would operate by saying, oh, yeah, this is one of those ones where there's an array of squares, and we got the tiles and with the coverings and stuff like that. So yeah, this is one of those ones where I'm supposed to use the invariant. Right? And wrong. It's just not. The argument fails. So this is part of, again, your job as students is to be thinking about the assumptions. What is it fundamentally that makes the algorithm work in a given scenario? What are the conditions? And then when you encounter one where those conditions aren't satisfied, it's part of your job is to notice that and to see that, it doesn't work here. Right. So likewise for the other two versions that I have in the circled right now. So if you remove non-opposite corners, or if you remove two unspecified squares of different color. Now just FYI, this one's pretty straightforward if you give it a little thought. This one's not that bad. Likewise. But this one here is actually a pretty challenging problem. Now, would I do something like this one on an exam in this class? And probably not. I don't know. It'd be a pretty challenging question. The idea that goes into solving number 6 is sufficiently different from the idea that I presented in class that I might decide, it's a little too creative, a little too much. Right? But nevertheless, it's a good exercise. It's a good sort of little, puzzle challenge question. And if you're curious, give it some thought and feel free to come to my office hours and ask me. I'll be happy to show you my answer to this one. There may be others. And now here's the last one I want to talk about. This is a really challenging question. 300 by 300, the tiles are now 3 by 1 instead of 2 by 1. And some truly creative thinking goes into the solution of this problem. And just a quick hint, you're going to not use the same invariant. You have to think about what is it that, how does the nature of the original question that we first saw, how does that relate to the shape of the tiles? And then, accordingly, when I change the shape of the tiles, how should I expect that to change the nature of the invariant, and possibly even the pattern that we overlay over the board. So this is a tricky one. Again, give it a shot if you like. Feel free to come talk to me if you're curious. Again, none of this will be on any exams. Okay. So, all right. So why do I show you all of this? I show you all of this because I want y'all to have a clear idea of what the nature of this class is. And a lot of people come into a class like this and have had maybe only high school math, AP credit, etc. And high school math is largely sort of plug and chug. I mean, it's not exact, right? But there's a lot of you need to know how to use integration by parts, and then they tell you what are the earmarks that you're going to notice that tell you that this is one where you're supposed to do the integration by parts algorithm, and then you do it. It is pretty pluggy-chuggy, right? So that's not really going to be how this class is going to go. Just FYI, right? What I'm going to be doing in this class, what you'll find in, I think, all of your math classes at Duke or elsewhere, wherever you might be, there's going to be creative work involved, right? You're going to need to understand ideas, and you're going to need to be prepared to play with those ideas. So heads up. Right, so on the exam, don't expect to just memorize algorithms and perform go through the prepared dance exactly as rehearsed. It's just not what this is. Okay, so stopping there for a quick moment. Does anyone have any questions about any of that? Does that all make sense? Okay. Feel free. All right, so let's do some math then. Well, honestly, this is math too, but let's do some multivariable calculus math. Okay, I should say let's do some Math 212. We're not going to be doing any multivariable calculus today. We have to lay a bunch of groundwork, define the world in which we will be doing multivariable calculus eventually. Right? So, very first thing we have to do is talk about Euclidean spaces. Now, the XY plane, I think you've all seen before. You might have even seen the coordinates called something other than X and Y. Right here I call them X1 and X2. Whatever. If you're doing economics, you'll see it, being P and Q, right? Or something. I don't know. It varies, right? Depending on what you're actually talking about. But the big idea is that you can talk about points inside of the plane. And every point you can think of as having a first coordinate and a second coordinate, and thus being defined by an ordered pair. Right? This is old news. Nothing new going on here. We define R2, otherwise known as the XY plane, as being the set of all such ordered pairs. Thus the set of all points in the plane. Right now, I'll point out that we already see one interesting thing here in terms of how mathematicians look at these sorts of things. There's a geometric idea that I wanted to model, right? The idea of points in a plane, and I want to be able to keep track of stuff like that. And then there's how do you say that algebraically, right? How do you say that without having to draw pictures and wave your hands? Right? So you're going to see a lot of this in math, that ideas can be understood from a geometric point of view and from an algebraic point of view, and it's very important to be able to sort of translate back and forth between them. A very large number of geometry problems are solved by taking the geometry problem, turning it into an algebra problem, solving the algebra, and then taking that algebraic solution and then reinterpreting that geometrically. Right? So we translate into the world of algebra because algebra is where we can do business. Very often, all exceptions granted. Okay. R3, same idea. Morally equivalent idea, right? We have a point in space now, and now there are 3 coordinates in I'm going to say the analogous way, in the same sense that I make a little rectangle there. Likewise, I'm going to make a little rectangular box here, and I can then describe that point with a trio, right? Not an ordered pair, but an ordered triple. And I can talk about the collection of all possible such triples, giving me the collection of all possible such points, namely all of three-dimensional space. Is that cool? Is everybody on board? Yeah. Now, where it gets creepy is when I say, yeah, okay, now let's do that with n coordinates. And a lot of people throw up their hands and say, that's not even real. Is that a thing? We're talking about the fourth dimension. What does this have to do with time travel? Right? It gets very sci-fi seeming, right? And, hey, slow down. That's got nothing to do with any of that. There's no Star Trek here. But the point is, you can still talk about ordered lists of not 2, not 3, but ordered lists of n real numbers. Algebraically, there's absolutely nothing creepy about this. Right? The only thing creepy is when you try to visualize it geometrically, and yeah, we can't do that. We're three-dimensional critters. We can't help it. Right? I would love to be able to think four-dimensionally. I don't really think anybody can. Right? But you don't have to be able to visualize it to be able to write it down algebraically. Yes?
What is that VI symbol at the end?
Oh, yes. Thank you. By the way, that kind of thing is going to come up where I use a notation where y'all might not be familiar with it. Please do ask. Thank you very much for that. I appreciate it. This upside down capital A is a little shorthand that mathematicians like to use to streamline the process of writing things down. It means for all or for every. Yeah. Okay, good. All right, so let's talk about vectors. Vectors, another idea related to n-dimensional space. A vector is a pair of things. It is a direction and a magnitude. So it's the both of them together. It's this pair, a direction and a magnitude. So here's some easy physics examples. I think the easiest one is the idea of a displacement. I was here, now I'm there, right? I moved by a certain amount, and of course when you move in a certain direction. So this is a displacement, is a direction that you've moved, and how far, distance being the magnitude in this case, how far have I moved in that direction? Oh, it's a vector. Other examples, velocity. When you are in the process of moving, instantaneous velocity, and I don't want to get into the physics. I'm going to assume that you all understand the idea of velocity and things like that. There's a direction in which you're moving, and there's the question of how fast or what is your speed with which you're moving in that direction. Now, speed is not a length, but it is a scalar representing more versus less, right? And so it can be thought of as a magnitude. Okay. Forces have a direction. Gravity pulls down, for bad or for good. Frankly, if gravity pushed upward, I think we'd all be in trouble. Right? So I'm going to call that a good thing in the big scheme of things. So it's a direction and a magnitude, right? There's such a thing as more force and less force, but they all have a direction. Now here's one, and this is a little weird. We're going to develop this idea later in the course, so let's not overthink this for the moment. But the flow of a fluid, right? Let's take the air in this room. The air is a kind of a fluid. I don't mean liquid. I mean it's a stuff that can move and that all kind of in some sense flows with the rest of it in some sense. So at any given point where you might happen to be looking, you can talk about what direction it's going, and you can talk about how much fluid is, how we make a magnitude out of this. We have options and units to worry about, and we'll develop that later. But there is such a thing as more flow and less flow, and so there's a magnitude of sorts. Okay. All right. So lots of important physical examples of vectors. Tremendously important concept in applying math to a multi-dimensional world, which of course is one of the things we're going to be doing in this class. Okay. All right. Now, real quick, I'm going to skip over one thing. I'm going to come down to this real quick. Keep in mind, a vector is a direction and a magnitude. Well, if you think about it, that arrow represents a direction, points in a certain direction, and by virtue of its length, there is an indication of a magnitude. So we usually use an arrow to represent a vector. But here's the thing, this arrow, now that's a different arrow. I can tell they're different because one of them's over there, the other one's over here. They're different as arrows, but as vectors, they are the same. And likewise this one, of course, and likewise countless others. These are all the same vector because they have the same direction and the same magnitude, and that's all a vector is. A vector is not a location. A vector does not have a location. It's just a direction and a magnitude. Does everybody see what I'm talking about here? Okay. Just kind of subtle, really. Okay. All right. So now that said, it turns out there is a natural correspondence between points and vectors, and I don't want you to overinterpret this. I am not saying that points and vectors are the exact same thing. They are not. Points have locations. Vectors don't, right? They are different objects. But there is a natural correspondence. There's a natural way to, if you give me one of one, then there's a sort of obviously related one of the other. So, for example, this vector, by which I mean that direction and that magnitude, which of course is exactly the same as that, which is exactly the same. This is a single vector that I've got drawn here. The association is this. Find the arrow representing the vector whose tail is at the origin, right? And that arrow will then have its head at a certain point. And this is the natural correspondence. The natural correspondence is between that point and that vector. So you give me a vector, there's an associated point, and vice versa. Is everybody on board? It's arbitrary, I suppose. The arbitrariness is in, where do I tie down the tail of the arrow? And I call this a natural correspondence because what point is more natural than the origin? That seems like the most. I could make it 3,17. That seems weird, right? The origin is sort of the clear and obvious natural choice. Okay. All right. So, a reminder, make sure you realize vectors have a direction and a magnitude, but no location. They do not have a location. By contrast, actually, let me leave this. Vectors of direction and magnitude, no location. Points have a location. But they don't have a direction. They don't have a magnitude. What direction is, Paris? That doesn't point in a direction. It's a place, not a direction, not a magnitude. That doesn't make any sense. Okay, so now because of the fact that these two things have a natural relationship with each other, but they have exactly complementary features. Context should make it clear which one you're talking about, so we can conflate vectors and points, and I'm going to do a lot of that in this class. I'm going to use point notation to represent vectors, and I'm going to use vector notations to represent points. Because, again, the context will always make it clear. If I'm talking about a location, which did I mean if I were talking about a location? Oh, well, then I must have been talking about a point. Because vectors don't even have a location. That wouldn't make any sense. Okay. All right, so let's talk about those notations. Of course, y'all are definitely familiar with this one to represent a point. Just an ordered pair representing the numbers. X and Y, or X1, X2, whatever the coordinates are, right? That's pretty clear. So this also then, very naturally, could be thought of as a notation for a vector. Now, some people like to indicate specifically that it's a vector to use triangular braces instead of parentheses. And you're welcome to do that. Our textbook does that. I don't really see the purpose of this myself. Again, the context should always make it clear which one you're talking about. So I don't, right? A comma B, right? And if I say at the point A comma B, or Bob is currently standing at A comma B, I didn't technically say point, but context, no doubt. Okay, another common notation to be aware of is putting a little arrow-shaped thing over, kind of as a little. It's like an accent. I guess you'd say it's a modification. Anyway, that little arrow is an indication, a reminder to the reader that is a vector, not a scalar. So as I have it drawn here, with V, with the little arrow over it, you know right away that that's not 4, because 4 is a scalar. Right, so this must be something. This is because of the little arrow over it. That's a vector. Is everybody cool with that? A lot of textbooks like to show off how cool their typesetting is, and they use bold. to represent that something is a vector, not a scalar. And again, I feel like they're showing off, and that this is all it does is make life harder for the reader, because the reader, can't, whoops, oh, I had my color set wrong. Reader cannot sit there and, do like that every single time. So it's just, I don't know, I think this is weird. It seems like it's creating a notation deliberately to make it hard for the reader. This seems counterproductive. I don't like this, but you'll never catch me using that other than to make fun of it. Right? So anyway, but nevertheless, you'll see it in this textbook and others, so be aware. And if you ever take a linear algebra class, some of you may have already had a linear algebra class, you might see vectors written vertically. There's excellent reasons for this, one of which we're going to encounter in a few seconds. But anyway, it's optional. Okay, pausing real quick. How are we doing? Questions? I know that I talk a lot and I talk fast, right? So I like to pause periodically, give you all a chance to squeeze a word in edgewise if you have any questions. Is everybody good? All right. Okay, moving along. We've already talked about how when we represent a vector with an arrow, we use the length to represent the magnitude. A length, of course, if you think about it, is also a distance, and a distance in particular, it is the hypotenuse of a certain triangle, and finding that in 2 dimensions is an easy formula. It's Pythagorean equation. I hope you all recognize this, so no problem. Now the notation here, notice that there's kind of double bars on either side of the vector. Another very common notation to represent magnitude is single bars, just like absolute values. And actually, it makes loads of sense to use single bars. It is mathematically analogous in the sense that if you think about what would a one-dimensional vector be, and were you to have a one-dimensional vector, what would be the formula for the magnitude? And it would be the absolute value. So it really does make a lot of sense, and it's nice. But frankly, I grew up, when I was learning this material for the first time, the course used double bars. I've just kind of gotten accustomed to it. I think it leaps off the page a little more dramatically with the double bars. I kind of like the double bars, but you're welcome to use the single bars if you prefer. Okay. A little bit of a geometry exercise that you can do for yourself. Is persuade yourself that in 3 dimensions, this is the formula. Now that's a little geometry problem, and I'll give you a hint on how to solve this problem. Looking at this picture here, this is not a triangle that we're looking at, but if you were to draw this edge like that, then you'll notice that we have a right triangle there, and we have a right triangle there. And if you write down the Pythagorean equation for each of those 2 triangles and then move things around a little bit, you'll find that you can confirm that this magnitude is given by that formula. So nice little geometry exercise, office hours if you have any trouble, and I'm going to leave that to y'all. Okay, how do we add vectors? Now, I'm going to do a very brief, I'm going to try to keep it brief, little philosophical aside. I don't want to just tell you what the formula is for adding vectors. I want to point out that this is a choice. When you make a definition, this doesn't come down from on high, right? This is, we get to decide what we want this to be, and we're creating. There is that creativity again. We're creating a new construction called a sum of 2 vectors. We get to choose what we want that formula to be. So what should our choice be? How should we motivate our choice? Very importantly, the way you should motivate your choice when you make definitions is you want your definition to dovetail, to fit in to link up in some way with something useful, something natural, something geometric or physical, right? We don't want to just write down symbols on the page because it makes it easy to write them down on the page. That's not a good motivation. Then you get arbitrary constructions. And I remember when I was a little boy, I thought it just made loads of sense that 4 times 7. Why should I have to memorize that? That's 28. That seems so weird. How about let's just do that. Boom. Now I'm an expert in multiplication, right? That would make life really easy, wouldn't it? This is tempting because it's easy symbolically, but it's also physically and geometrically meaningless, right? So this is a bad idea. That's the third grader thinking, right? Right? So we don't want to accidentally do that. So here's what I propose. Let's think of vectors as displacements. This was our very first physical example of a vector, right? And if a vector is a displacement, and if your first displacement moves you in that direction by that amount, a second displacement, wouldn't it make sense to think of it as just sort of following, sort of concatenated with the first displacement? If the second displacement is to move in that direction by that amount, oh, wait a minute, but we've already moved by the green vector. So there it is, same vector, same direction, same amount. Then here's what it would mean to concatenate two displacements. And altogether, notice that, whoopsie. Oh gosh, okay, let me just do it again. Altogether, if I do the green displacement followed by the blue displacement, grand total, I started here, I ended there, and therefore that is my total displacement. So I propose this is what V plus W ought to be, because this makes sense. This is natural in the context of a natural example of vectors. Does that make sense? And then the geometry to algebra, not hard to persuade yourself that if your first vector has those coordinates, your second vector has these coordinates, then the sum has those coordinates. So that's the resulting algebra. Again, very importantly, this comes first, and that then motivates the algebraic formula subsequently. We don't define vector addition this way because we like how this formula looks on the page. We do like how it looks on the page, but it's not why we made the choice. We make the choice because we like how that connects to a physical example. Is everybody happy? Right. Okay. Moving along. Oh, by the way, this is a great example of why I like this vertical notation. Notice that we're just adding across the rows. Right? If you write your vectors vertically, this looks really natural. Okay. Among many other reasons. Okay, similar thing. If you're going to displace by a certain amount in a certain direction, what would be C times that? And I propose C times moving a certain amount in a certain direction would be to move C times as far in that direction. So you draw this picture that motivates this formula. I think that's pretty believable. I think that algebra is pretty believable. I'll leave that to y'all to think about the geometry of that. Is everybody happy with that? Okay. Now here's one that is a little tricky. Here's our first theorem. If you scale a vector, its magnitude gets scaled by the absolute value of the original scalar. And at kind of first glance, why the absolute value? Because it may be a little confusing to think about. This is very easy to prove, though, and the critical tool, well, two critical tools. One critical tool is to notice I have formulas for everything on the left side of the equation. How to multiply a vector times a scalar? Boom, I've got a formula right there. right? How to compute a magnitude. How do we compute magnitudes? Formula on the previous page. So I can straight up write this all down in coordinates. And likewise, I can straight up write all that down in coordinates. And then you can just check algebraically that this is true. Exercise for y'all to crank through. The other critical point, and a lot of people get this wrong, is to make sure that you understand how square roots work. This is dramatically misrepresented in a lot of contexts as square roots undoing squares. Nope, they really don't, right? Half the time they do. But any negative number, when you square it and then say this symbol, aka square root, you get the absolute value of the number, not the original number. Right? Anyway, this is an important thing to understand. Again, a common misunderstanding about this symbol. This symbol means the positive square root. It doesn't mean pick whichever one you want, right? And it doesn't mean look earlier in the question and choose on the basis of where this expression came from. That's just not what that symbol means. This means non-negative. So if you want to indicate the negative square root, you have to write the little minus there. And if you want to indicate that you're interested in both, you have to write the plus minus. Right? So I hope that makes sense to everybody, but make sure that you're clear going forward. What this symbol is that I have highlighted in blue is specifically the non-negative square root of whatever is on the inside. Okay. All right. Now, subtraction. How are we going to define subtraction? Right? Seems like we've got a new choice to figure out, but if we want algebra to make any sense at all, notice that subtraction is a combination of multiplying by scalars and adding, right? Where the scalar is -1. So we've already decided what scalar multiplication does. We've already decided what addition does. So we have, in fact, inadvertently already defined vector subtraction. And here's a picture that I think makes sense. A pretty easy way to remember this is that this plus that. And let's think about it here for a second. What should W plus V minus W equal to? Well, I certainly would hope that that would equal to V. Whoops, there we go. Right, so from a vector addition point of view, this picture ought to be a thing, and as such, that gives us an idea for how to think about V minus W. And I like to think of it also related to this picture. Think of vector addition as taking your first vector, and the act of adding W says I'm going to take the head of V and move the head as indicated by W. Likewise, subtracting W suggests that I'm going to take V, I'm going to identify where the tail is, I'm going to move the tail of V. That's just a different way to think about it, your preference. Okay. All right. Everybody okay? Let's see here. By the way, this class, 9:30 to 10:45, is that right? Okay, so we're doing great on time. Okay. Some algebraic properties. This is a bit of a bore. I don't know about y'all's elementary school experience. When I was in elementary school, they went to a lot of trouble to make sure that I understood that this was called the commutative property of addition, which seemed like a whole lot of words to say something that was perfectly obvious. And why would we bother to put such a big sounding name on such a painfully obvious thought, right? It seemed very, very trivial. I mean, stuff like this, that obvious, why do we even bother writing it down, much less naming it complexly? So here's the thing. Real numbers are not the only kinds of objects with which we do operations and define algebra. Right? And the algebra that we create for other kinds of objects, at some point, not so obvious. Right? There's a bunch of algebra of matrices, for example. Some of y'all may have seen. I won't assume it, but And the algebra of matrices is not quite as obvious as for real numbers. And some stuff doesn't work out the way you would think. So anyway, we write this stuff down just as to recognize what it is that we are allowed to do. When we're manipulating algebra of vectors, it's important to know what you're allowed to do so that you don't accidentally assume and then do something that you're not allowed to do, because that's where mistakes come from. Okay, so I think these are all pretty clear. They're all pretty easy to prove. I want to encourage you all to make sure that you can prove all 5 of these properties. It's not hard. I'll tell you the approximate strategy, and that is going to be, let's take this one for example, to write the left side in coordinates, write the right side in coordinates, and then use existing facts that you already know about algebraic properties of real numbers, because those coordinates are real numbers. And so those coordinates themselves, you can do all of your old favorite, commutativity, etc. The punchline then is by breaking it down to coordinates and using known properties of real numbers, this follows pretty quickly. So it's a good practice problem, though, to write that down. Make sure that you understand what's going on there. And again, as always, if you're not sure, if you get stuck, if you're confused, if you have a question, come to office hours. Right? That's a good way to get questions answered. Okay, a couple of details that have to get said. A unit vector is a vector whose length is 1, thus the name unit vector. Turns out that unit vectors are very useful in various ways. So that's all that means. Here are some examples. This is a particularly important unit vector, easy pitch, that the magnitude of this is 1. Right? But this is one of what we call the standard basis vectors. And I'm going to go ahead and write this down. If you are in, let's see here, if you're in R2, then, oh, you know what? We're in R3, aren't we? Okay, here we go. There, now we're in R3. This vector here is a vector that points exactly along the x-axis. It's a unit vector pointing along the x-axis. This makes this the first standard basis vector, we call it. And then the second standard basis vector is along the second axis, again, unit vector. And then the third standard basis vector is along the third axis. If I could draw straight up there, forgive me, there we go. That's along the third axis. So standard basis vectors. I don't know if y'all may or may not have heard that term before, but we're going to be using that a lot. Now here's another. Oh, real quick about notation. In a lot of classes, this gets referred to as I. The little roof hat that is being used here is also kind of standard sometimes as a reminder to the reader that this is not just a vector but a unit vector. The little hat thing, the little roof-shaped little hat is a notation for that. But you don't have to put it there. A lot of people don't. I don't usually myself. You can just call it I. And then likewise IJK for the others. Reminder though, sometimes we're not doing math in R2 or R3. Sometimes we're doing math in R17. Again, don't try to visualize that. Your brain will not, right? But nevertheless, you can have a question that has 17 variables in it, right? Take an econ class. You'll have like 7 different variables in a question. Independent of whether you can or can't draw the picture, which you can't, you're still doing math in R7, and then you start to run out of letters if you use IJK. You'll have IJKLMNO, and then what if you're in R37? Well, now really don't have enough letters. So the great solution is to use subscripts, and this is the standard choice here. E with a vector arrow over it with subscripts. The subscript tells you where the 1 is. So this subscript being 1 means that the 1 is here in the first position of 3. In this case. Does that make sense to everybody? Okay. I like to keep things general as much as possible, so I tend to use this myself. Okay, easy pitch that this is a unit vector. Nice little fun fact about arithmetic. 3, 4, 12, 13 is a Pythagorean quadruple. So anyway, it's a fun little exercise in arithmetic to go through and confirm. Okay, one useful fact that you can do with the idea of unit vectors is note that for any non-zero vector, v, if you take that vector and divide it by its own magnitude, the result is not only always a unit vector, but it's always a unit vector pointing in exactly the same direction that the original vector was. We're going to use this a lot. Very often I need a unit vector pointing in the direction that was given to me by a non-unit vector. So that's how you do that. Neat little trick, easy to confirm. Let's confirm that this is a unit vector. If I want to confirm that something's a unit vector, I need to take its magnitude and confirm that I get 1. That's what it means to be a unit vector, right? So you can see that this, we're going to win this this little thing here. So how do I know that this is true? Well, I have here a scalar. Scalars factor outside of magnitudes by way of including an absolute value. This is clearly positive, non-negative. Right? In fact, it's clearly positive. This can't be 0. It's got a 1 for a numerator. So positive number, absolute value of a positive number is just that number. So the absolute values go away. And then these cancel, and again, victory. Is everybody good? Okay. All right. A little bit of terminology. By the way, it's very often the case when you're doing math that you have to there's certain definitions that have to get said, certain quick and easy little obvious little facts that have to get established so that you can eventually go on and do more powerful things. But anyway, so forgive the seeming triviality of a lot of this. We just got to get it done. But here's another little sort of statement that just has to get made. A linear combination. Very fundamental construction, especially in the subject of linear algebra. If you've ever had a linear algebra class, you would know this. Otherwise, you'll certainly see it in a linear algebra class. It is a sum of scalar multiples of vectors. So here you'll notice that we have a bunch of vectors. Notice I'm taking scalar multiples of those vectors, and then I'm taking a sum of those scalar multiples. So this is just the way we sort of verbally say it. A linear combination is any expression of this form. And it turns out, again, to be very, very useful in linear algebra, very, very useful in dealing with vectors. And one of the reasons for that is this statement down here. Notice that if you use the standard basis vectors, right? There is that notation that we talked about for standard basis vectors. Any vector ABC is a linear combination of the standard basis vectors where I use the coordinates of the vector as the coefficients in the linear combination. It's really easy to show. Now again, I encourage you, write this down. If you can see it in your head, that's great, right? But make sure you're crisply clear why this is true. And it's just a matter of writing down what these vectors are, write them down in coordinates, multiply this out, add up the terms, and you'll find that you get this as your result. Okay. Is everybody comfortable with that? Okay. All right. Okay. So, moving along. By the way, I think we just finished one section of the book. So, good news, bad news. You have homework tonight. Moving on to the dot product. Now again, the question of multiplying vectors, philosophical. This is not, handed down from on high. We get to decide how should we, what do we want to be the formula for how to multiply vectors, and we want it to, in some sense, we want it to kind of dovetail, fit in. We want it to connect to geometry somehow. We want it to be natural in some way. The problem is that answering, this sort of immediately, how should we multiply vectors, is it'd be a pretty deep pull to just write down what ends up being the correct answer. So what I'm going to do is I'm going to write down the answer first, and then I'm going to persuade you later, by which I mean in a few minutes, how this formula really does connect very nicely with geometry. First thing I should say, though, it's going to turn out there's actually a couple of really good answers to this question. There are a couple of constructions that we can write down that, as it turns out, really are very geometrically natural, and furthermore, that behave algebraically like multiplications. So we're going to have two kinds of products. Thus, the importance of always indicating which kind of product. You can't just say multiply these vectors. There are two different multiplications. There are two products. If you say multiply, then you effectively haven't said exactly what you're doing. Okay, so this first one is called the dot product. Here's the formula. If you have a couple of vectors, coordinates given, like so, then the dot product, given by this notation right there, is computed by that formula. Now, it looks weird. I mean, you can see a kind of a multiplicative aspect on multiplying sort of the like coordinates, first times first, second times second, etc. But very importantly, I'm adding those products. I don't get a vector. It's not V1W1 comma V2W2, etc. Right? We're adding them to get a scalar. That's very strange to think that two objects, that when you multiply them, gives a completely different kind of critter. It's not the same thing, right? This is perhaps your first time seeing such an example. So that's the first thing to make sure you understand. And again, I seemingly pulled this out of thin air. You should be suspicious, right? Maybe deep down you trust me, but at least, as a formality, you ought to be, okay, yeah, but he owes us an explanation of why are we writing down a seemingly arbitrary formula. Right? Okay. All right. So what I hope will not persuade you very much is that it does have some easy algebraic properties we can write down. Now again, these all have to be checked. Don't think to yourself that you already know that this is true. I saw the commutativity of multiplication in elementary school. Oh no. What you saw in elementary school was the commutativity of multiplication of real numbers. That's not what these are. These are vectors. And this multiplication you did not see in elementary school. I wouldn't think so anyway. This is the dot product that we just wrote down. It's a brand new operation. Just because I choose to write it down with a notation that looks familiar does not mean that it behaves the same way. Right? So this is something that has to get proved. Now again, you write it down in coordinates. Do the left, do the right. Works out. Everything's fine. It's easy to prove. Again, come to office hours if you're not clear how to go about doing those that check. But it does need to be checked. Not obvious. Is everybody happy? Okay. All right. Okay, so I say you should not be impressed by this. This is, guess I'm kind of glad that this dot product we've written down has some nice algebraic properties, but you might amuse yourself to try to think of other arbitrary formulas that you could write down that would have these same properties. And it's not that hard to even dream some up. So there are plenty of useless constructions that behave nicely algebraically, right? So that's not. This is not good enough to be persuasive that that we're onto something good here. The geometric properties are where I think it starts to get persuasive. That this is natural. This is geometrically natural. The first one is an easy one. Very important fact to be aware of: the dot product of a vector with itself is always magnitude squared. Now I say that this is a geometric property because magnitude is an intrinsically geometric thing, right? So our formula that we've made for dot product, at least in this sense, dovetails with geometry. Everybody happy? Okay, here's a weirder one. This is called the Cauchy-Schwarz inequality. So again, dot product, again, connects to geometry. So again, that's kind of cool. What is a little disappointing about the Cauchy-Schwarz inequality is, well, the fact that it's an inequality. It's not a, dot product behaves exactly, it equals, there's a certain amount of slack, in an inequality. But nevertheless, this is a true fact. It is geometric, and side note, it's also really useful in a lot of ways that will show up more so beyond this class, but here and there in this class. Yeah.
Can you explain how less than the operation acts?
Yeah, how it could be?
Yeah.
Oh, well, yeah. Here's an easy example. Let's look at the vector v. Being 1, 0, in which case the magnitude here is 1, right? And then I'm going to let w be 0, 1, which makes this magnitude 1, but the dot product of these is 0. So yeah, does that make sense? Yeah. So it is an inequality. The left side and the right side not only will not always be equal, they are usually not equal. Right? But the left will never be greater than the right. And that's the sort of the eyebrow raiser. Great question. Anybody else? Okay. Here's where I think it starts to get really persuasive, really impressive. And that's this formula right here, that the dot product equals, right? None of this inequality sloppiness. Equals. And then everything on the right-hand side is geometric. Magnitude is a geometric thing. Angle is a geometric thing. Everything on the right is geometric, and the dot product is exactly computed by that intrinsically geometric formula. So I think that's okay, all right, well that's undeniably strong connection to geometry. Now, what it isn't is something I can draw a picture of, right? I can't draw in this picture here. I mean, I can see the magnitudes. I can see the angle right there. But where's the dot product in that picture, right? I mean, when we did vector addition, here you go, yeah. When I did vector addition, where's the sum in this picture? Well, bam, there it is. I can see it in the picture. There's the thing, right? There's the thing I'm defining. We don't have that here. So that's unsettling. And I was uncomfortable with this for a long time when I was in y'all's position. But what you eventually realize is that you don't technically really need that. I don't need to be able to see a picture of the thing I'm talking about if I know at least that it has relationships to things that I can draw pictures of. So, again, a little unsettling. It's okay. All right. Yeah. Okay, now how do we prove this fact? And it's a nice little exercise in sort of geometry and trig. And by the way, I know y'all have all probably had a class in trig. And I feel sure that your class in trig included a statement about the law of sines and the law of cosines. And I'm fairly sure that they didn't come up much. Other than the test if you knew the law of sines, the law of cosines. FYI, they come up here and there, not necessarily a lot, but man, when you need them, they're really useful, right? So good things to know. Make sure that you're comfortable with, for example, the law of cosines. And here's how I'm going to use it here, given a couple of vectors, v and w, and then I'm going to look at their difference, v minus w. Weirdly, what I'm going to do, well, let me not get ahead of myself, but I'm going to take that v minus w and I'm going to compute its magnitude squared, because that's part of the law of cosines, right? The law of cosines is this statement here about the magnitudes and the angle in that triangle. So flashback to high school trig. If you didn't see the law of cosines in high school trig, you're welcome to come to my office hours. I'll show you. And I'm sure there's also a billion references online that you can look at as well. Okay. All right. Now, but here's the thing. Magnitude squared of that difference vector, v minus w, we also know from the previous page, I can think of as a dot product of that difference with itself, because dot product with itself is a magnitude squared. That's one of the first observations we came up with about dot products. So the beautiful fact then is that I've computed something two different ways. This thing is equal to this, but it's also equal to this, and therefore these two things are equal to each other. This is what I like to call a mathematical bank shot. We weren't actually interested in magnitude squared of v minus w. I don't actually care about this at all. But computing it two different ways has allowed me to get information about things that I am interested in. And so then you notice that you can, by the way, you can cancel, you can kind of multiply this out. Just using the established properties of dot product. And then we can cancel that, because again, don't forget, we know that these are equal. And then we can cancel that with that. And then I can cancel this common factor of minus 2. And lo and behold, we're done. And we have that that is equal to that. Like so. Everybody buy it? Cool. All right, so it's a cool proof. Thank you, law of cosines. Another exercise I'm going to leave for you all. Take this equation, take the absolute value of both sides, and what will fall out is the Cauchy-Schwarz inequality. Another exercise to leave for you all to work out on your own. Again, if you get stuck, if you're not sure how to actually put those pieces together, come to office hours. I'll be happy to show you. Another, for your consideration, this being the first day of class, strategically in this course, you are welcome and encouraged to work together on, certainly on these, all the things that I say in class. Hey, exercise for you all to work out on your own. You don't literally have to do it on your own. You're very welcome to group up. Okay, let's do the thing with the Cauchy-Schwarz, like you said, and help each other, right? I think that's a fantastic way to learn. And I think I said this in the introductory recording that you all have already heard, so I'll be brief. But receiving an explanation from a friend, colleague, classmate is, of course, obviously a useful thing. But giving the explanation is fantastic practice in communicating mathematical ideas. And that is a really important skill on exams, right? To be able to communicate your mathematical ideas without kind of, hand waving and saying, well, come on, that kind of thing, right? You want to be able to just idea to idea to idea to idea, boom, answer, right? So think of, anytime you get asked to help a friend, help a classmate out with understanding an idea, that's an opportunity for you to hone your ideas, your understanding. All right. Okay, so let's look at this example right here. The question says, how do I compute the angle between two vectors? Well, notice that angle is something you can solve for in the above equation. And so, given that you have these two vectors, well, you just compute, and out comes the answer. Everybody happy? Yeah. Right. Okay. Some easy facts. You all remember about cosines and how cosines work. And so, you can look at the dot product and draw conclusions about angles. When the dot product is positive, that means that the cosine is positive. And think through back to trig. If the cosine's positive, what does that mean about the angle? Turns out it means that the angle is an acute angle. Now, again, flashbacks to trig. Make sure that you can fill in those details. And then likewise, negative means it's obtuse. And if it's 0, that means that the cosine is 0. What angle is it that makes the cosine 0? And that is a right angle. And that would mean that these vectors are perpendicular. Is that cool? Now there's a little detail devil to be noted. I was assuming that the vectors are non-zero. Okay, well, so if one of the vectors is 0, or both of the vectors are 0, the weird thing is you can't really talk about an angle, right? So if you think about it, I can talk about, well, here's a vector and here's a vector, and I can talk about the angle between those two vectors. But on the other hand, if here's a vector, and now let's look at the 0 vector. What's the angle between those two vectors? Well, the zeros, it's not pointing in a I don't know what direction that you're talking about. It's not long enough to define a direction. So we can't talk about the angle there at all. Right? Now the dot product will be 0. The dot product of anything with the 0 vector, let's look at the arithmetic, it's going to be 0. But you can't say that it's a right angle, because there is no angle. Right? So this is an awkward, unfortunate little thing. So we use the word orthogonal to mean that the dot product is 0, and this orthogonality, then this is actually two possibilities. It could mean that there's a right angle between two non-zero vectors. Yeah, sure, absolute could be. But it also admits the possibility that maybe one of them or both of them are the 0 vector and there is no angle at all. But of course, obviously the dot product is 0. Yeah.
What's the difference between like a 0 vector and just a point?
A point has a location.
So if like a 0 vector, like if we associate that, like I guess in a question with the location would be the same or no? Okay,
so the context is always key, right? And so if it says, Bob is standing at 0, 0, well, then we're talking about a point, right? But if the question says, assume a displacement of a comma b, and then later on in the question, turns out that a and b are 0, well, that means your displacement is by 0, 0, which means your displacement is the sort of the trivial displacement of not moving. And the act of not moving does not have a location. Does that make sense?
Yeah.
Yeah. It's weird. Yeah, right. Okay. All right, so easy little algebraic example. And I'm now looking at the clock and realizing I've been out of time for 3.5 minutes. I'm sorry, I didn't mean to go over there. So calling it for today. We'll pick up here on, not tomorrow. Tomorrow's 4th of July. Have a happy holiday. Play safe with the fireworks. See you on Wednesday.